68. Okay, we are headed into molality and colligative properties. Remember, I told you we were working with two concentrations that were really, really close to each other, right? We just finished doing what? Molarity. Okay, let me have all your attention up here because this is important. Okay, we just stopped working with molarity. We're still going to have molarity on the test. So how am I going to tell the difference? Remember that little ditty I told you? Molarity, milliliter, molarity, milliliter, molarity, milliliter, moles per liter. You can use that. You can also use molarity with capital M, right? It looks to me like mountains. And in between the mountains, there's always a lake. So moles per liter. That's how I remember it. If you don't remember the ditty, just think of it, it's a mountain and there's a lake between, so moles per liter. Molality is what we're heading into now. It actually is a italicized M, and I purposely say it like this, molality, because that sounds fat to me. Okay. Also, I write it like this because it looks like a bunch of fat rolls. Okay, so it reminds me it's moles per kilogram. Moles per kilogram. So this is on your first day 5. This is what you're writing down. You're writing down this equation. So it is, molality is moles of solute over kilograms of solvent. That's different than molarity. Molarity is of solution, and we'll talk about that in just a second. So I gave you a couple ways to remember. Molality, it's a cursive italicized M, and it looks like fat rolls, so it's moles over kilograms. Okay, because that's how the doctor weighs you, is in kilograms. And it's a solvent. Now, that same thing is right here. There's only one difference in between molarity and molality. It's one letter. Okay, it's the R versus the L. So but there's a difference also in the actual reaction or the actual equation. This one is solution. So remember the mountains and the lakes. This is of the whole solution, so it's a whole area. Okay, but molality, which is our cursive italicized M, it's just of the solvent. Okay, and we're going to go through and be working with those. So somehow in your notes, help yourself to remember which one's which. I've tried to give you a couple mind tricks to remind you, but you got to remember which one's which, because if you use the wrong one, it's not good. Okay? Molarity is what we usually use when we're doing concentrations of stuff in lab. Molality is what we're going to be using in what we call colligative properties, which we're going to talk about in just a minute. So let's do a couple of problems. So here it says, what is the molality of a solution that has 6.44 grams of barium chloride dissolved in that many grams of water? Yes?
So there's
molality? Molarity?
Yeah. Does that one deal with liters and the other
Yep. Right. Yep. Okay, so the first thing I need to do is I need to be able to find moles. So I want to take that barium chloride over here. Look up barium on the periodic table, and it is in the second column. It's number 56 coming down. It is 137.33, and I have just one of them. And I have chlorine, where I have 2 of them, and chlorine is right next to the noble gases. Yep, and we've used it a lot, so some of you've got that memorized, which is awesome. And we're going to add that up to find out how many grams we have in 1 mole of that substance. How many? 208.23 grams of barium chloride in a mole, per mole. Okay, so then I can take that 6.44 grams over here, and I'm going to set up a factor label because I've got to keep track of my units. And I want to get rid of grams, so I'm going to take that 208 and put it on the bottom. And I know that I added it up and it was equal to 1 mole of that same substance. So I can then cancel out grams of barium chloride. Then I just put in my calculator 6.44 times 1. I really don't need to times it by the 1. And divide it by 208.23. So what do I get for an answer right here? 0. What? Say it loud for me. 0.3. Give me one more. Okay, and that would be moles of barium chloride. I'm not done though yet. What did it ask me for? Molality. What was molality again? Oh, that was that fat roll thing. Moles divided by kilograms. So we just found moles. We're going to take that moles and we're going to divide it by our 455 kilograms. What do we get? Yes? Okay, and that would be molal, barium chloride. And I like that he put it in scientific notation. If your calculator didn't, you would probably end up with this, with 4 zeros, 684 molal. So it gets a little hairy with the zeros when we get too big. Okay, how are we doing? We doing okay? A little confused. Where are you confused? What can I go back over for you? Okay, so take it one step at a time. I gotta find out how many grams are in it. Found out how many grams are in the mole. Change the grams they gave me, 2 moles. Once I've got those moles, I went really far ahead. Try it again. Once I've got those moles, then I take those moles and divide them by the kilograms, which that is not the one I was using. There it is, and I don't know why it's not staying. Okay, well this is the next one. It's giving me the answer to the old one. So I just took my moles and divided by kilograms. I'm going to erase this. I want you to try the practice on your own. I don't know why it's showing me the answer to this one on the practice, because I'm just going to erase it for you. Yes. Why? Depends on what the nickname is.
I was just like, came up in my head for some reason. I just wanted to know.
I've been called Chem Mom.
Oh, let's call her Kimber.
Okay, let's see how you can do it. See if you can do it on your own. We'll do it here together in just a minute. I want you to see if you can do the practice on your own. I'm going to start real slowly doing it, so if you're lost and you have no idea what to do, you can look up and see. So I would carry 3 or 4 until you get to the end. Yes?
So if I'm rounding, would this become 1 and then...
I would probably carry 0.6077.
Okay.
Got to be careful. This is grams, not kilograms, so you got to change it to kilograms first. So it's 1 point what? Does anybody have the final answer? 0.15? Okay, sorry. That would be okay. You probably are off a little bit by rounding. Okay, so it's not really hard, same kind of stuff. We don't have to add anything on the bottom though for this one. We got to be careful. We're not adding anything on the bottom for this one. Okay? It's just whatever the solvent kilograms are, that goes on the bottom. Okay? Okay? We're going to move forward. Wait. Okay, write it down quick. No, you're good. Where did I lose you? So we walk through it again? Okay, so they gave me 529 grams, but the equation for molality is moles divided by kilograms. So I had to change it to kilograms by dividing by 1,000. You know, I'm not always going to spoon feed you. Okay, we all right to go forward? Is everybody still copying down? So this part right here, I changed it from grams to kilograms by dividing by 1,000. And then I took that answer and I put it up here to divide because I'm using this equation. Okay? All right, anybody else? Before I go on, do you understand this? Make sure you understand it because we're going to be using it. Okay, we're going forward. So when we have, guys, when we have aqueous solutions, how do you know you have ions in the aqueous solution? How can I test for that? Okay, in solutions, when we have ions, they're also known as electrolytes. Have you ever, as you've been on a sports team or something, they say, drink some Gatorade, drink some Powerade. Okay, why? Or when you're sick. Because when you're sweating so much, have you ever noticed that sweat sort of salty? It gets in your mouth, it's sort of salty, sort of nasty. Your body, when it sweats, is getting rid of some of the electrolytes. The electrolytes are what makes your body talk to each other, your body talks to each other. So if it gets rid of too much electrolytes, your brain can't tell your heart, pump. Your brain can't tell your body, you know, idiot, you've done too much, I'm going to shut you down. So we need those electrolytes in order for our body to function. And electrolytes, all they are is ions. Yes?
So you said if we had too much electrolytes?
No, if we don't have enough. Because the electrolytes are what move us around. But if we have too much, then it can cause a problem too. Yeah, you can. All right. So, strong electrolytes basically are salt. So we just use salt. Did you need anything or you're good? One more time. Okay. Okay. Okay, let's focus back up here, please. Back row. Thank you. All right, so when we have strong electrolytes, that's when we have ions. So we have a positive and negative ion. When we don't have strong electrolytes, we have what's called non-electrolytes. This would be like sugar. It still looks like it dissolves, but it doesn't conduct electricity because it doesn't have a charge. Okay? So ethanol, ethylene glycol, which is antifreeze, those things don't conduct electricity. Okay? So we're going to play a game. I'm going to see, remember how we talked about when we had the ones up here, they were called type 3, we called them type 3 here, but it's basically two nonmetals bonding together, and we use the monoditri, like carbon dioxide and silicon dioxide in their names. Those ones are non-electrolytes. They don't do a positive and negative charge to hook together. Okay, but other things on the chart do. So let's see if we can figure this out. Is sucrose an electrolyte? Is it going to make ions? Or a non-electrolyte not going to make ions? Okay, electrolyte up, thumbs down, not electrolyte. It is a non-electrolyte. Anything with carbon, hydrogen, and oxygen is going to not collect all your sugars, all your oils are all non-electrolytes. Okay, well, how about this one? Electrolyte or non-electrolyte? It is an electrolyte. We're going to do another one. Let's see. Good, this is gasoline. Okay, what about this one? Okay, some of you aren't voting. Okay, it is an electrolyte. Okay, we got two more. Let's see what they are. It is. Okay, and this one, last one's tricky. You ready?
No.
Okay, how come you say no? Well, it can still have oxygen and be an electrolyte. What you need to look at is where they are in the periodic table. So silicon and oxygen are really close together. Because they're close together, it's going to be covalently bound, which is not going to have ions. Okay, so that one is not an electrolyte.
Wait, did they tell you to take salt packets because of the electrolytes?
Mm-hmm. Okay, all right, so let's go forward. So as we were talking about Powerade's a good thing, or Gatorade's a good thing to get electrolytes back in. They were made for sports teams. Now, to replenish electrolytes. But if you're just drinking them to drink them and you haven't been exercising and losing electrolytes, you're actually putting too much in. It has a lot of sugar, yes. Usually the sugar's there to help get the energy back real quick. So we do need electrolytes to maintain cellular function and making things work. But if you have too much, it can actually shut down cellular function. So you have to be careful. Use electrolytes as needed, but water is great until you need those extra. So we're going to go into what's called colligative properties. This is where we make solutions. Tell me what a solution is again. What was the definition of a solution? We've made them. What are they? Solute and a solvent, right? Solute is what? What's being dissolved, and solvent is? What's doing the dissolving. So when I have a solution, that means something's inside a solvent, right? Then these four things happen. We call them colligative properties. The vapor pressure lowers, so we call this Rayleigh law, and we'll go into each one of these in a little bit more in detail in next slides. Freezing point depresses, gets lower. Boiling point elevates, gets higher. Osmotic pressure is possible, and I'll tell you what that is in a minute. Oh, did everybody get those four written down? Sorry, we'll talk about each one of those. Oh, I think they're already written down for most of them. Okay, so when we talk about vapor pressure, when it says vapor pressure, if I have a sealed container and there's a space above, like when you have a pop, okay, there's so much of that pop that's, or that gas that's coming out of solution and is above the pop in the pop bottle. If I add stuff to the pop, like Mentos or something like that, then things change. The solute actually stops things from coming out. So I did a bad example by Mentos because it releases the gas fast. But if I put like a whole bunch of salt, I wouldn't want to drink it, but if I put a whole bunch of salt in the pop bottle really quickly and put the lid back on, there would be less pressure up here because I put more stuff in. So that stuff prevents the gases or water from coming up and making a vapor pressure. So as we're looking at it, if we actually measure it with what's called a manometer, we put a container of just solvent, measure it. We put solvent and a solute, and we measure it. It actually doesn't have enough pressure to push the manometer mercury down as far as if I had a pure substance. Okay? The reason is it's sort of like blocking. These desks are sort of like the blockers if I'm trying to get to the door. If the desks weren't here, I could go straight out, right? But with the desks here, I have to go a roundabout way and try and make it out. It makes it slower. Yeah. Okay, so vapor pressure lowering. So what would you put down for vapor pressure lowering? You got to put something. What are you going to put? You're going to put a pitcher, one of those. Okay, basically less gas above the liquid when I have a solvent. More gas above the liquid when I don't. When I have just a solvent and not a solute. When just one thing, when I just have a pure substance, I have less. When I have a solute and a solvent, then I'm going to have less pressure above. Okay? I'm going to have more pressure when it's just a solvent. Okay, then we get to osmotic pressure. This is really, really, really important for kidneys, for dialysis machines, and everything like that. It is, you can see this little line right here. This right here is a semi-permeable membrane, meaning some things are allowed through and some things are not. If they're small enough they can go through, they'll go through. If they're not, they're forced to stay on the other side. So our bodies use kidneys like that. They allow waste that's small enough to make it through and go out, but they keep in red blood cells because they won't want red blood cells going out of the body. Okay? So what happens is it moves from always areas of high concentration, areas from dilute to high, because it's trying to make on both sides of the wall, make it even. So it's sort of like balancing a classroom. If I've got all you guys in here, but the classroom next to us only has 5 and they're teaching the same thing, they'll try and balance that classroom by taking some of you over there. Does that make sense? Okay, this is really important for how our body works, moving things in and out of cells and in and out of our kidneys. Okay, so if I were to take a solution, and we actually do a lab like this in 1110, where we take dialysis tubing and we put concentrated sugar water or salt water inside the dialysis tube, and then we put it in some water and see what happens. What happens, to start with, they're equal, but after time, the dilute side tries to dilute the more concentrated side, and so we've got movement going. And that movement is known as osmotic pressure. Okay? Now, in your own words, write down, what is osmotic pressure? Anybody got some ideas? What would you write down? Yes? To dilute concentrated side, okay. Through a semi-permeable membrane. That's important. What? Actually trying to make it isotonic, which is the same on both sides. Okay? All right, so it's trying to dilute the more concentrated side by moving water through semi-permeable membrane. Okay, then we get to boiling point and freezing point depression. Well, freezing point depression, boiling point elevation. Remember this chart, our phase diagram? Solid, liquid, gas, remember this? Okay, see how this blue line, this was our what? Our melting point, freezing point, right? I did push it. So this is our melting point, freezing point line. Notice how it moves closer to the y-axis. And our boiling point line moves closer to the x-axis. So our area where it's liquid increases. That's what happens when we add a solute to a solvent. Okay? So we use that in our cars. We put ethylene glycol or antifreeze in our cars so that our water in our radiator doesn't freeze when it gets too cold, and it doesn't just turn to gas when it gets too hot. We've extended the range that it's liquid. Okay? So in real life, other than using it as antifreeze, we actually put salt on the roads to lower the freezing point of the ice so that it will melt and go away. We also use it to put in our macaroni and cheese to make macaroni and cheese so that we can boil the temperature of water at a higher temperature, and so we don't end up with mush. If you've ever taken, this is the biggest mistake of first-time backpackers. They take macaroni and cheese up to the mountains, and then they go to boil it. Well, the boiling point in the mountains is lower than here, and even if you add a ton of salt, you end up with mush and not macaroni anymore when you're trying to boil it. So, yeah, MREs work great, except they're heavy. So you got to be careful. All right, so this is the equation we are going to be using. You need to write that down. You don't eat macaroni and cheese when you go up in the mountains, unless you take the Velveeta already done stuff that you just heat up. Okay, you do that. I've been backpacking enough to know that that's an issue. Okay, so we're writing this equation down. You got that equation written down at the top of the page above that, or right below that chart. Delta T just means change in temperature. K is a constant. If I'm working with freezing, it'll be the freezing point constant. If I'm working with boiling, it'll be boiling constant. The M here is our fat rolls, molality, moles per kilogram. And our I is how many parts will it break into. And we'll talk about that in just a second more. We are going to be using water the most, this one and this one. In the chart that you have, it also gives you the boiling point of water, which is 100 degrees, and it gives you the freezing point of water, which is 0. If we were using some other compound besides water, for instance, benzene or acetic acid or something else as our solvent, then we would have to use the melting and boiling point of them. But we're going to keep it basic and just use water. Okay? Everybody got that equation written down? So delta T equals KMI. And it's the italicized cursive M. Just right below the chart, it says equation. Okay, we got it? Okay, we got it written down? All right, going forward, we're going to use this equation. If you didn't get it written down, there it is again. Okay, what? The I is known as the Van Hoff factor. And the Van Hoff factor is just the number of particles it will break into. And for covalent compounds, that's type 3 when we're naming it, like silicon dioxide, NaT, and sugar. Those are 1. They won't break apart. For ionic compounds, it's the number of ions it will break into. So glycol is an organic molecule which is covalent. So the I here is 1. For NaCl, NaCl will actually break into Na plus and Cl minus. So I have 1, 2 particles they'll break into. So I here is 2. What about calcium chloride? CaCl2. I'm just doing some examples right now, and then I'm going to have you do yours. CaCl2. I'm just doing some extra ones. So I have 2 Cl minuses that are extra. So I have 3 things here, so the I is 3. Now the bottom one's a little tricky, and it will catch you. You've got to remember that polyatomics are covalently bound. They stick together. But this compound is an ionic compound. But I cannot separate the PO4. Okay, so I have 3 Ca plus 2s. So I can write 3 Ca plus 2s. Okay, there's 1, 2, 3. And I have 2 PO4s. So PO4 minus 3 is 1, PO4 minus 3. No, I'm just showing you how to get it. So how many total do I have? How many total do I have? 5. So I here is 5. The biggest mistake I see is people go, oh, that's 3 and 2 and 8, that's 13. No, there's only 5. Okay? So let's look at the next one here. We'll come back to the other part. So find this part on your thing. I think it's back the page. Okay? I want you to take a minute. I want you to find the I's on your own. I want you to tell me how many I's. Remember, here's a little hint. Anything with carbon and hydrogen in it probably is a 1. Because it's like oil. Okay? All right, so take a minute here. Just a minute. I'm only going to give you a minute. And write down what you think the I's are for these. If it has carbon, or hydrogen, it's probably 1. Not just oxygen. Oxygen can be or cannot be. It depends on what it's with. Yes? How far away from the noble gas it is. So, like the first column, we minus 1, second column, minus 2, third column, minus 3, fourth column could be plus or minus 4, and then you go on this side, plus 3. D's can be lots of different things. Beryllium's column plus 2, lithium's column plus 1. Okay, let's see how we did. That's about a minute. Coming back. Believe it or not, I've been watching the clock. So, sodium chloride, we did that already. How many? 2. Because it had an Na plus and a Cl minus. 2 parts. So, it's a 2. What about C6H6? It is a 1. It does not separate. What about C2H5OH? That is also 1. That is ethyl alcohol. This is a benzene ring. What about MgCl2? 3. Mg is plus 2. We have 2 Cl minuses. So total 1, 2, 3. I equals 3.
Number 5 is 4.
Okay, we have a 4. Is it a 4? Anybody else have a different? I have a 2 and I have a 5. Ooh. Hold up. Okay. It's a 7 or a 6. Wow.
It's 5. It's 5.
Okay, remember what I told you. If you have a polyatomic, that polyatomic's going to stick together. So I have K plus, which is an ion, and I have NO3 minus, which is an ion. So the I here is 2. So you got to remember, if it's a polyatomic, it's going to stick together. That's why that one's tricky. And ClCl4 is, why do you say 1? Because of the carbon?
What is it? Because there's more of the other one in it makes it single?
I don't know. What do you think? You think there's 2? Okay, anybody have a different one? And I have a 5. And you have a 3. Okay, let's look at where carbon and chlorine are. Are they close together on the periodic table, or are they far apart? They're close together because they're close together and both above the staircase. Remember, the staircase tells us if they're both above the staircase, that's the monoditri area for type 3. I is 1. Okay, does everybody understand each one of those now?
Yeah, I got this.
Okay, so now I'm going to have you put your head on, a thinking cap. If you were a city manager, okay, city managers have a specific budget. They also are in charge of making sure that the roads get cleaned when it snows, but they've got to keep it within their budget. Let's look at the I of each one of these. What would sand's I be? I would be 1. What about rock salt? And what about calcium chloride? 3. 1 calcium and 2 chlorines, right? 1 calcium, 2 chlorines. Okay, now, what about money-wise? Which one's the cheapest? Sand's the cheapest. Okay, what is the most expensive? Ice melt. So we're going to go like here for ice melt. And this one is probably in between, right? Okay, so think about this. This I tells me how much it will lower the freezing point of something. So if it's not very cold outside, I can use sand and it will lower the freezing point by 1.86. Okay, that's 1 times. If I use rock salt, it'll double it. If I use ice melt, it will triple it. So if it's really, really cold and I've got really nasty, messy, icy roads, I got to use ice melt. But am I going to use ice melt throughout the city? Only high traffic areas. Everybody else will get sand, if they're lucky. Yeah, good question. If I mix them, I can save some of my resources. So I could do a sand salt mix, which is what they do. And I can do a sand, rock, salt, and ice melt mix. And I can get even a part that's not quite as low as just ice melt. But having put just ice melt on the road is really, really expensive. Okay, so good thinking. Let's go on. We're going to do some changing in boiling points. So we're going to do some calculations. So here I've got this much dissolved. Oh, lucky you guys, it's already given me moles. Okay, in this much grams of water. So first thing I need to do is do what? This one I think you're going to have to add on. So just put it somewhere, because I can't remember which ones are on there and which ones aren't. Yeah, I'm sorry. This one gets a little bit. Okay, so we're going to first of all need to find molality. Remember that molality is moles per kilogram. I like this example because it's really simple. I need this to be in kilograms. What do I do to put it in kilograms? Divide by 1,000, right? So I divide by 1,000, it becomes 0.520 kilograms. Everybody okay with that? Any problems with that? Stockton? Okay. He must be working too much. Okay, so up here we're going to put 1.00 moles, and we're going to divide that by 0.250 kilograms. Well, 1 divided by 0.25 is 4, right? There's 4 quarters in a dollar. That's how it helps me remember it. And we would put molal of glycol. Well, they want the new boiling point of the solution. So this is where I bring in that other equation, which was the delta T K M I. And freezing point. I just need to bring in the right constant. So I'm going to look up in that chart KB for water. So look in the chart. What is the KB for water? 0.512, isn't it 21? Is it 12? Okay. 0.512 degrees Celsius per molal. That's my KB. My molal is right there. Glycol, what did we decide was the glycol? The I. This would be 1. Okay, so plugging in everything, 0.512 degrees Celsius per molal. Whoops, that's a times. I don't know why the rest of it's going away. This board is being fun with me. 4.00 molal times by 1. Okay. What about it?
Is I always 1?
No, it's 1 here because glycol, if we remember, we already talked about it, glycol is an organic, so it's a 1.
Wait, so
It won't come apart.
always 1.
Organics are a carbon-hydrogen mix, and that'll be a 1. So that's part of our type 3. Okay, so somebody put this through the calculator. What are we going to get for our delta TB? 2.05, okay? Now, is that my new boiling point? That's just the change. What was the original boiling point of water? 100. So we just add 100 to this, and we get for the new boiling point 102.05 degrees Celsius. Done.
Why are we doing that?
Because. Okay, so going forward. It's so nice to finally put that in. Oh, I forgot. I already did it for you on here. Okay, so since it's water, we use the 100, okay, to add to it. Now, what if we do want to find the freezing point of that same solution? Remember, boiling point was elevated, so it's higher. Freezing point's depressed. It's lower. We're going to subtract it, but we have to use a different K.
No.
Yep, so we have 2 Ks we've got to remember, the boiling point one and the freezing point one.
Oh, that's easy.
Okay, so KF, we're using the same equation. It's delta T equals KMI, but the K we use for freezing point is different than the K for boiling point. So we're going to still use our lovely little equation and plug in. Okay, and what are we going to get for our change in freezing point? Somebody plug that through your calculator. Let's see what it is.
Yeah, I think so.
These are extra examples that we're just doing because I didn't get the examples before she printed it. Okay, so we should end up with 7.44. Is that what you got? Okay, this is my change in freezing point. What was freezing point originally for water? 0. And if it's depressed, what's it going to be? We're going to take it away from 0. So it's going to be lower than 0. So we add a negative in front. We got the new freezing point of water. Pretty good. Okay. Going forward, thinking about it. Okay, this one already threw in the answer beforehand, but I think this one's on yours. Is it on yours, this one?
No.
Nope. Okay, we'll apply it again. The I here for sodium chloride, Na plus, Cl minus. 2 particles. I is 2. Okay? We already have the molality and the Kf. So we just plug those through. Times them together. Not a hard thing. Okay, guys, stay focused. Okay, we're going to get 20.1 degrees Celsius. Since we're doing freezing point depression, we're going to take it away from 0, and we're going to get negative 21. You're going to want some examples, so make sure you've written some examples down, guys. So we're going to get a bunch negative. We're going to be doing these in lab next time, so we need to make sure that we're getting how to do this. I will put it up, yes. It'll actually be up on Canvas, not the web. But yeah. It'll also be on my YouTube channel, too.
Could you also go from this wall? Oh, that's right. You have to try to secure it.
You'd need to know how, you need to be able to figure molality. Okay? Okay, shh. Here we got another one. Determine the boiling point if I've got this dissolved in water. So we've got this much of this, and we've got this. Let me see if I've got this one. Nope, I don't. Okay, so let's walk this through. Calcium chloride. What's the I? I heard it. 3. How did you get 3?
That's the one calcium.
1 calcium, 2 chlorines. I got 3. I can do that fast, right? I don't have to add anything up except, wait a minute, I got to be in moles, right? So I'm going to have to add it up. So I have a calcium, 40 point, what was calcium? 40.078. And I've got 2 chlorines. How do I know when it's supposed to be in moles? If I'm trying to find a new boiling point or freezing point, I've got to have molality. And molality is moles per kilogram, right? So I'm going to add this up. Somebody add it up real quick. Yep. While we're doing that, while you're adding that up, grams has to be in kilograms, so I'm going to divide that by 1,000, and I'll get 0.555 kilograms. Everybody okay with that? 110 point. Okay, that's how many grams of calcium chloride is in 1 mole. So the other thing I need then is to figure out how many moles I've got. So I'm going to take 46.5 grams of calcium chloride, and there's 110.98 grams of calcium chloride in 1 mole. Calcium chloride. Change colors. What do we get for the mole? Okay, that's good. That's moles. And how are we going to get molality? Moles per kilogram, right? Here's my kilograms right here, so I'm just going to take that and divide it. This is chemistry. Okay, what do we get? 0.9 what? 0.75? One more. 0.7? Just 0?
5.
Oh, another 5. Okay, that's my molality. Now, they asked for the new freezing point and boiling point. So this is where I go back to the equation, delta T equals KMI, right? So for the boiling point, the change in temperature of the boiling point is going to equal KB, which is this number. Whoops, let's try that again. 0.512 degrees Celsius per molal times by molality, 0.755 molal, times by, what was I? 3. Okay, what do I get? You got an answer? This whole thing, boiling point. Yes. Okay, 1.16 is the change, so I'm going to add that to 100. So my new boiling point is 101.16 degrees Celsius. That's part of the answer. What else did they want? The freezing point. Not hard, guys. Change in temperature of the freezing point, we're going to go 1.86 and times it by the same things on the other side here. Okay, what do we get? Yeah, one's freezing, one's boiling. I'm still using the same stuff. I'm just figuring out what the new boiling and freezing point are.
So instead of putting,
So instead of using the 0.52, I use the 1.86 right here. Okay, so what do we get for delta TF? Okay, degrees Celsius. But what do I need to do here to get the new freezing point? Subtract it from 0. So it's negative 4.21 degrees Celsius. Done. Okay, that's the answers. Done. Okay, so the boiling point was elevated, the freezing point was depressed, and it would have osmotic pressure, and we would also be having lowered vapor pressure. Okay, so that's all we're doing for today as far as that goes. I'm going to flip this back for those that were still doing that. Now, what? Same thing, same equation. We just use the KB instead of the KF. Okay, now, I need you listening. I need your lab notebook or lab right up in front of you. We are going to do something that the other chemistry classes are not going to do next time, but only if you are able to finish your lab next time quick enough. We're going to do the application of the freezing point depression, which is making ice cream. But you have to do your lab first. That means I'm going to give you the information to do your pre-lab today. That needs to be done so you can have it stamped off, and so you can go back in lab, get your lab done, and back in here in enough time to make ice cream. Okay, the other classes are not doing it. So listen up. I'm going to give you and your lab partner your chemical, and you have to research it. There's computers up here, or you can use your phones. Okay, you two, you're doing cornstarch. You two are doing sugar, but you're doing C6H12O6. Okay, you guys are doing rock salt. You're going to do rock salt. Okay, there might be another one, so listen. If there's another group doing rock salt, you can go in with them. But I like to try and do two. You guys in the back are going to do magnesium sulfate, MgSO4. You guys up here are going to do baking soda, which is NaHCO3. NaHCO3. You guys are going to do sodium carbonate, which is Na2CO3. You guys are going to do potassium sulfate, which is K2SO4. You guys in the back are going to do a funky compound. I'm just going to give you the formula of it. It's Na2S2O5. Okay, coming back up here, you guys are going to do calcium phosphate, Ca3 parentheses PO4 parentheses 2. You're going to do borax. I'm not going to tell you what the I is. You've got to figure it out. Okay, you guys are going to do cornstarch again. Next one back, you're going to do sugar, C6H12O6 sugar. Okay? Yes, that's the one you're going to use. You're going to use rock salt. She's going to use rock salt. Okay? You're going to use salt. You're going to use magnesium sulfate, MgSO4. Yeah, they're just over there. I didn't grab them. And you're going to use sodium hydrogen carbonate, which is baking soda, so NaHCO3. You guys are going to use calcium phosphate, Ca3PO4 parentheses 2. Ca3PO4 parentheses PO4 parentheses 2. Yeah. And you guys are going to do borax. Okay, yes. Which one was yours? Baking soda? Yep. Yes. You got to figure it out. Yeah, that's what you're supposed to do. I did not. Borax I didn't do either. And cornstarch I didn't either. Yes. So how many parts will this break into? That is a polyatomic, and that is not.
H
So
will always be 1.
no, this is part of this group. So if you look on the back of your periodic table, that is a group.
Okay.
So that's 1, and that's 1. So okay, so you guys had the calcium phosphate. So you have 3 calciums, 2 phosphates. Okay. You what? Yeah, I'm grabbing it. Sorry. Where did I put it? Oh, it's on the floor here. I didn't get it all the way back. Ugh. Okay, your box is back there so you can turn in your assignments. Guys, make sure that the pencils get back in the basket for me, please.